Hello everyone, I thought I would do a simple little video today, probably no more than about 5 minutes, on just this really interesting video I stumbled on about a year ago. It's by Josh Levine, and it's called, or titled rather, Amazing Example of Complex Emergent Behaviour from a Very Simple Rule. And oh boy is that rule actually really simple. The rule, in to be expressed as just a single sentence, would, a very simple sentence, would be if flash, I flash more, or I wanna flash more. And it's an expansion on this 2006 paper here, and the only parts I'm gonna actually look at is this. Fireflies can simply be abstracted as oscillators that emit a pulse of light periodically. This type of oscillator is referred to as a pulse-coupled oscillator, and also you study biological systems such as neurons and earthquakes. I didn't know earthquakes were biological systems. This section describes how time synchronization is achieved in a decentralized fashion between these oscillators. Now, the thing I love most about this is it's decentralized, which means there is no communication between any of these flashes. And then there's a graph here that sort of shows you what's happening here. So this guy's fired, which means he wants to fire now. Or, I apologize, I've read that wrong. So I apologize. So as you can see, there's a graph here. Now this represents a creature's, we're going to call them creatures here, or no, we'll call it an oscillator's urge. So the oscillator here goes up and up and up, and once it hits the top, it fires, and you can see it sort of fires for a brief sec, and then it resets back down to 0. And then what happens here is it goes up and up and up, but then look, this one just fired here. So what's happened here is it's jumped up because it wants to flash now, which means it flashes sooner. And you can imagine when this happens over the time t, it will eventually sync up. Now, bear in mind this this delta phi here. Is that psi? Oh, I need to remember my Greek alphabet. I think it is phi. This delta phi is not constant. It is a percentage. So expressed as code here, it would be this function here. So simply what we're doing here is I'll actually run it first so you can see what it looks like visually. You can see these are all our flashes. Now, the darker the circle, the less urge there is to flash. The brighter the circle, the more it wants to flash. So you can see they all start off random, but over time they're actually syncing up. I think this is 16 members of this population size. We can see that that group has already synchronized. That's incredible, because that happened quick, and they were all random to begin with. Now I'd call that synchronized. So what we're doing here is we're checking here. We're checking the distance and making sure it's beneath at least twice the range. And then if we find an urge that's greater than or equal to 999, we're going to set our urge to our urge plus a tenth of our current urge, or plus 10% of our current urge. We're increasing it by 10%. And this very simple rule, just this here, is what allows these guys to sync up. Now that is an incredibly efficient rule. Yeah, so what I'll do is I will head back down to here, and we can see this works for almost any population set. There is a condition, however. You can't really have these bundled up tight. You can, and they will sync up, but it leads to a very sort of weird behavior. In my simulation, this is what it came out to. This sort of initial sort of linear kind of process, and then flatlines to an almost random state. What it should look like, however, is this. And this is a population of 64, so you can see it's actually sublinear. So if we were to take the gradient of this, it would actually get less and less as time progresses. So looking at this, I was like, okay, that's really interesting. What if we get 128 in this population? And this is what it came across. Now looking at this looks like a square root of n. and would obviously be the population size, and the result would be average number of flashes. Now, for my use case, how I decided what the average number of flashes would be, or how I'd calculate it, is I picked a member from the population set, and I would count how many times he flashed until every single one was synced up. And the way I would tell if they were synced up would be to, let me just find it here very quickly. Yeah, we'd just put in an error there of 25, and then just see if it's synced up. That's how I would tell. Very, very simple. Which is what I love about this discovery here. Is it's so simple, yet it achieves such consistent results. It really is mind-boggling. So what I will be doing is I'll be making this public. I'll be making this source code public on GitHub. I'm gonna try and optimize it a bit more, divide the space occupied into grids, so we're not checking the entire space, we're just checking the local grid. That should make it a lot more efficient, and hopefully I'll be able to plot up to 1,000 members of our population, because just calculating up to 128 took me, I think it was about 3 hours on my old laptop, which is, it's not the fastest. It's like a AMD Athlon, but it did take a while. And I will also add parallelization for when we are just running a simulation and not running it visually. So there are two modes. There's a visual one, and there's just a data plotting one, which saves it as a CSV file. But yeah, I just thought I'd show you this because I found it and I loved it, so I hope you guys love it just as much. Have a good day.